All right, in tonight's lesson, you're going to learn how to model exponential growth and how to model exponential decay. Why might this be important? Well, maybe you want to find the balance of a bank account, or maybe you're a chemist or an archaeologist and you want to be able to predate the age of the bones or the DNA that you've discovered based on the half-life. So exponential growth and decay actually have some really applicable real-life scenarios. Let's look at this scenario. In 1990, Florida's population was about 13 million. Since 1990, the state's population has grown about 1.7% each year. This means that Florida's population is growing exponentially. Why? Because it's growing at a percentage every year. So on year one, it starts at 13 million, and you have to take 1.7% of that and add it. The next year, it's whatever the year before was, plus another 1.7% of that year. So you get this sort of compounded effect that it's going to continue growing at an incredible rate per year. All right, so I have two different variables going on here. I have population growth and I have time. Which one is my x and which one's my y? Well, remember that x is independent and y is dependent, meaning that x can be whatever you want it to be, but that determines the value of my y. So let's think about this. Is population my dependent variable? Does population determine my time? No, time goes on regardless of population. So time is going to be my x, and population is going to be my y. And let's keep in mind that we're talking about population in terms of millions, and we're talking about time in terms of years. So those are the units that I'm working with here. All right. Furthermore, if I want to find Florida's population in 1991, so my population is going to be y, and that represents the number of people in the millions. Okay. So y is going to equal my 1990 population, which was 13. Again, we're talking about millions, so it's 13 million. So y equals 13 times, I've got to multiply the population growth by, well, what's 1.7%? Remember that 1.7% is the same as 1/7, move the decimal back 2 places. And I'm dealing with 0.017 as the actual number. Because when I get rid of my percent sign, I'm dividing by 100. So I'm going to multiply my population not by 1.7, but by 0.017. And frankly, I have to add it to, if it's growing by this each year, then I'm adding 1.7% to the actual population of the previous year, or the 100%. So it's increasing exponentially. Every year I have to multiply it by a 1.017. Where'd that 1 come from? Well, 100% equals 1.0. Remember, 100% is the same as 100 over 100, which equals just 1. And if I'm adding an additional 1.7% every year, I'm having to add this 0.017 to my 100% every year. So that's where this comes in. This is 101.7 as a percent. And then ultimately, this changes based on year. So at my initial time, it was simply 13 million. Year one, it's going to increase by 101.7%, and by year two, it's going to increase at 101.7%. So this brings us down to our next problem. By 2000, what was the population of Florida? Well, I started in 1990. So in 1990, my population was 13 million, roughly. By 2000, I want to know what my population is. How many years have elapsed from 1990 to 2000? Well, 10 years. So again, years in time is my x. So that's my 10. If x equals 10, what is y? Well, let's plug my 10 in for x, and what do you get? Hopefully you followed through your steps here, and you started by plugging your x value of 10 in for your x value right up here. And then remembering your order of operations, you did this whole thing first, which gave you this answer. And then you multiplied that by 13 to give you your final answer. So what was the population of Florida? Roughly-ish 15.4 million people. That's about a 2.5 million increase in 10 years. Pretty substantial, even though that percentage looked pretty small. All right, enough about Florida. Let's look at how we model exponential growth and the function that we use. So exponential growth is modeled by the exponential function of y equals a times b to the x power. Oh, this looks exactly like what we did before. So let's clarify these terms a little bit. So let's look at this. Remember that a represents our starting amount. It's the base start. So when I looked up here at Florida's population in 1990, that's the first date I'm given, its population was about 13 million. So 13 was kind of ground zero. It's where it all started, at least as far as my function is worried. So my starting amount when x is 0, or when my time is like right at 0, that's my a value. Okay, that's this part right here. So what is b? Well, b is my growth factor. What? It's your growth factor. You take the percent that something increases and you turn it from a percent into an actual number. So my growth factor, when I was talking about this, was the previous year plus another amount. And so that growth factor is what went right here. It's the amount by which my population increases. And when my population is increasing and it's adding to the original amount, it's always going to be a 1 point some amount. It's always going to be 100+%. It's never going to be under 100% or we're dealing with decay. Okay, so then I get my exponent. And my exponent in most situations, my exponent right here is equivalent to the time, from the difference from 1990 to 2000. It's the in another word, it is your independent variable. It's what affects your y. What changes your y value? That's your x. All right, let's look at this situation right here. Since 1985, the daily cost, the daily cost of patient care in community hospitals in the United States has increased about 8.1% per year. In 1985, is that my A, my B, or my X? Well, X is generally time. So we're talking about since 1985. Oh, yeah, okay, this is X when X equals 0. So in 1985, such hospital costs had an average of $460 per day. Oy. Okay, so in 1985, hospital costs averaged 460. If X is 0, this is my original time, then looking back up here at my equation, I need a starting amount and a growth factor. So let's see if we can find our starting amount. Hopefully you notice that if 1985 is my beginning time, then the cost that it gives me there is my beginning cost. So 460 per day is my starting amount. So let's go back and see if we can identify our growth factor. Well, we notice it increased, so we're dealing with exponential growth, not decay. And it increased at about 8.1%. All right, right here. This is the amount that it increased. This is my growth factor. All right, let's see if we can write our equation now to model this. So the two variables that I'm dealing with are the daily cost of care and the dollars, right? That unit is dollars. I'm sorry, or time. Time is my other unit. Because I've got years. 1985, 1985. All right, so I want to model. I need to find some way to figure out what A times B to the x power looks like with this equation. All right, so if I notice up here that I've got time, then I'm going to let my x be the number of years since 1985. And y is going to be the cost of care. Well, why is it this direction and not backwards? Well, let's think. Does cost of care end up depending on the number of years? As in, am I waiting for next year to come? Will January of 2018 not come until the cost of care is increased a certain amount? No. The year's going to come regardless of how much it increases. So x is my independent variable. Y is dependent. The cost depends on how many years have changed, according to this statistic right here. All right, I still have an A and a B I need to deal with. So my A is going to end up being the starting amount. Well, the starting amount was the initial cost in 1985, also known as $460. My B is my growth factor. I've got 8.1%, and it's growing, so I have to add it to 100% because it's never going to go below 460. 100% of 460 is 460. So I end up with this B being something like 108.1%. And I need to convert this to a decimal. So I'm going to end up getting rid of my percent sign by moving this 2 places this direction. So I get 1.081. Remember that 108.1 over 100 means that I move my decimal 2 places. That's how I got this 1.081. That's my growth factor. All right, so now that I have my growth factor, I have my initial, all of my variables, let's plug it in and see what we end up with. Y equals 460 times 1.081 times x, where x is the number of years. Okay, and I like to use parentheses around my 1.81 and my growth factor just so I'm really clear about the fact that my exponent goes only to this guy, and I have to do this first. All right, so let's see what the cost, if this trend holds, what would be the daily cost of hospital care in 2015, 2 years ago? Well, 3 years ago. So in 2015, the cost of care would be, first, I need to find the difference between 1985 and 2015. How many years have passed? Well, 20 years. Wow. Okay. So again, my years are my x value. So I'm going to plug 20 back into my equation. Y equals 460 times 1.081 to the 20th. What does this give me? All right, so it gives me a really long decimal. I'm just going to truncate it or cut it off after 3 places. So I get 460 times 4.748. What is that? Remember that you're doing your exponent first and then you're multiplying. And it gives me $2,184.08. Oh my goodness. So in 2015, the cost of care daily. So if I had to stay in a hospital for an entire day in 2015, it was going to end up costing about $2,184. That's a big change from 1984 when it only cost $460. It's pretty impressive. All right, I'm going to give you an example that I want you to do that's just like this. Suppose your community has 4,512 students this year. The student population is growing 2.5% each year. Write an equation to model the student population. What will the student population be in 3 years? Go ahead and make sure that you can identify your y, x, a, and b. Write an equation. Make sure to transfer your decimal to a number. Make sure you're adding it to 100%. And then write your equation to model and tell me what the student population would be in 3 years. Hopefully you're going to get some number between 4,000 and 5,000. That's the only hint I'm giving you. I'll check it tomorrow in class. Well done. Thanks for hanging with me for this.